Okay, in this exercise, we're going to algebraically add together a couple of vectors, and then we are going to find the magnitude and direction of those additions. And actually, we have a subtraction as well. So we have a couple of vectors defined here. They give us the magnitudes of their components. So AX and AX is 1.3 centimeters, AY is 2.25 centimeters, BX is 4.1 centimeters, and BY is negative 3.75 centimeters. And it's not that the magnitude is negative 3.75 centimeters. This actually has some direction to it. The x and y subscripts here refer to standard Cartesian coordinate system where x is to the positive x is to the right and positive y is upwards. So this simply just means that it's 3.75 centimeters and it's going to be in the negative y direction, right? So first off, it might be a little bit easier to kind of organize these vectors, writing it out in a little bit more compact notation with the just vector notation there. So I could say, vector A given in vector notation here is, I use this kind of angle bracket here, and I write it out as, kind of AX comma AY, right? And then you put your magnitude out here. So the x component is 1.3 centimeters, the y component is 2.25 centimeters. So we'll write it out here as 1.3 and 2.25. And my units here are centimeters. Put them out there, okay? So that's vector A, I can describe that way. And vector B, I can describe the same way. And so the x component there is 4.1 centimeters, and the y component is negative 3.75 centimeters. Okay, so there's A and B. And they want us to first find the components of the sum A plus B. So I can call here, let's say the resultant vector R is equal to vector A plus vector B, okay? Which is as simple as just adding the components together to each other. So really, if I have them kind of on top of each other like this, I can just kind of put this bar down here and add up straight down, right? But you have to be very careful. You can only add x components to x components and y components to y components. This is why we first break things into components before we add them up. So I have the ax is 1.3, the bx is 4.1. Just adding these together, I get rx is going to be equal to 5.4, right? And doing the same thing with the y components, I have 2.25 plus the negative 3.75, right? So we get here, this is negative 1.5 centimeters. So this is, this is the solution to the part A. The components of the vector sum is, Rx here is 5.4 centimeters, and Ry is negative 1.5 centimeters. I just want to, let me kind of graphically go through this addition as well to kind of just illustrate what's going on here graphically. So we have vector A, like AX is given, scroll down a little bit actually. So, AX was like 1.3 centimeters. I should draw this 1.3 centimeters long, or I can have a scale. So AX was 1.3 centimeters. AY was 2.25 centimeters. So this is AY should be a little bit longer, and that's going to go in the positive y direction, right? AY. I can add these together. Obviously, if I start out, with AX like this, and then at the head of AX, I place the tail of AY. That's AY, and then my vector A looks something like this, right? So going from the head of AX to the tail of AY, or, I could add it the opposite way given the commutativity of vectors if I wanted to. So that's really vector A, something like that. but we're not just finding, and of course I can use trig to find magnitude and direction of vector A, but that's not really what we're asked to do here. But that's vector A, and then vector B, Bx was given to us as 4.1 centimeters, so that's a bit longer. This is Bx, and By was a negative 3.75, so a length of 3.75. Too long maybe. And downwards, right? So this is By. So, you know, and obviously if I want to get really accurate, I can draw these to scale. But vector B is going to look something then, I guess, like, let me see, I can actually just move By over. There we go. And so then I get this is vector B. It looks something like this, right? And if I wanted to add A and B together, I guess I can take then vector B. I guess I can just do something with this moving. Well, I moved part of it there together. And I can do vector, you know, A and B together, and I get something along the lines of, you know, that's A plus B. But that's, you know, not entirely accurate because I'm just sort of sketching here, right? You know, the components up here are much better. But you actually look to see my sketch. This should be 5.4 in the X and negative 1.5 in the Y. It's a little bit off. I think I got the X decent, but the Y should have actually been negative. Probably should have been down over here somewhere. But these are very rough sketches. But what happens when I just add up these components? Given here my AX, AY, BX, BY, which I'll need to redraw. The BY looks something like this. You know, I first add in the AX and the BX, then the AY and the BY. And so we have, I'll just move these. So if I take I'll start out with AX as kind of my first one, and then I'll add BX to AX, right? So placing the tail of BX to the head of AX there. Then looks like that. And then I can add in AY and BY. So then I'll add, you know, AY, the tail of AY at the head of BX now, right? And then, okay, let me figure out how to just get off of that. And then if I then move BY, and I'm going to place the tail of BY at the head of AY, and it kind of like undoes a lot of AY, but that's okay. And then I end up here slightly negative, right? So we end up, this is another color. This is going to be my resultant of AX plus BX plus AY plus BY added all together, all these vectors, and it looks something like this. And this is my resultant R, which is what we came up with over here, which looks much more accurate, right? So that's, you know, kind of, you know, graphically really what we're doing. We're actually breaking it up into, we have these kind of 4 vectors, and then we add all 4 of them together. Now we had, you know, vector A and vector B were both given to us in component form, like this. If they weren't, and we needed to add them together, there would be a step before this, in which case if vector A was defined this way, with some magnitude, let's say the magnitude of vector A, I'm just, you know, roughly doing it here, might be like 2.7 centimeters or something like that. And then the angle here is maybe, oh, I don't know, 75 degrees, something like this. Just sort of, that's a guesstimate, so don't take that. But if it was given this way, with a magnitude and an angle, first I would resolve it into components to get these, then I would add it together. And I have to break it up into components first before you can add them together algebraically. Okay, I'll run through the rest of these more quickly here. Part B says find the magnitude and direction of A plus B, which is, what we had here, right? So that's r. And so I need to know, what is this magnitude, what's this magnitude here, and what's this angle, right? And you look at it and you say, oh, okay, this should end up in the fourth quadrant, so I should get a negative angle or somewhere between 270 and 360 degrees, right? So, just looking at it here, I have, my opposite is going to be the y component. My adjacent is going to be the x component. My magnitude I can get from Pythagorean theorem, so we can get the magnitude of r given this, what we have here in component form. This is just going to be the square root of rx squared plus ry squared, so we have 5.4 squared plus, this is negative 1.5 squared, which is really just 1.5 squared, right? And this magnitude ends up being 5.6 centimeters, the magnitude of the resultant. And then to find this angle theta, I can just take, given that I have my y component and my x component, I have these, right? Y component, x component, I can just take the inverse tangent of that. So theta is going to be equal to the arctan of, we have ry over rx, so negative 1.5 over 5.4. This ends up as, your calculator will, for the inverse tangent, it's going to spit out angles that are between negative 90 and 90, right? That's your range for the inverse tangent. And so this is negative 15.5 degrees. Or if I wanted in standard position, then, so that's this one, negative 15.5. Standard position would be 360 plus negative 15.5, so that's, what was that, 344.5 degrees. Okay. So we can say that vector r, this resultant vector, is equal to 5.6 centimeters. You can either say at negative 15.5 degrees, which would be, standard position, but it's in the clockwise direction. Or we could have said 5.6 centimeters at 344.5 degrees. Either way, I would accept. Unless it says something like, what is the counterclockwise angle it makes with the positive x-axis, you'd have to report it this way. But I would accept, if unless otherwise stated, I would accept negative 15.5 or 344.5. Okay, moving on to, now we have the vector difference b minus a. So let me take what we have here. B was, I'll just rewrite it down here. So vector b was given to us as 4.1. And I'm going to start with b on top because I'm doing b minus a. I'm just kind of lining up like doing, just simple arithmetic here. So 4.1 and negative 3.75. Make sure I put my units here. Okay, I did for the magnitude, just making sure. And then A was 1.30 and 2.25 centimeters. So then when we do B minus A, I'll just simply subtract A from B, right? So we have 4.1 minus the 1.3. So this is going to be, I don't know, I'll call it D. This is vector D, which is B minus A. Just for a difference vector. You can call it anything you want, really. So the 4.1 minus 1.3, what is that? 2.8. We have 2.8. And then negative 3.75 minus 2.5, that gives us what, negative 6.00 centimeters. So there's part C, I believe it was, the components of the vector difference done, just like that, just with some subtraction there. And then the magnitude and angle, I have Pythagorean theorem, right? So magnitude of D is going to be the square root of 2.8 squared plus, I'm just going to call this 6 squared because it's the same thing. And this is equal to 6.62 centimeters. This is the magnitude of vector D. And then the angle it makes, theta, I will use the inverse tangent of my y component over the x component, so -6 over 2.8. Before I even do this, let me think about it. Positive x, negative y should be fourth quadrant again, right? So we have here negatives. This is negative 65 degrees, which, puts us in the fourth quadrant, right? So, can say this is actually negative 65 degrees would be the exact same thing as 360 plus a negative 65. So what does that put us at? 295 degrees, right? So 295 degrees. And so we can say that vector D is equal to, looks like a B, 6.62 centimeters at 295 degrees, or at negative 65 degrees. Either way, there's probably this equals theta. This is really what was asked specifically. This, you put them both together like this, so I'm perfectly fine with that because you're given, the answers. So that's part D kind of put together. Okay.